RFID technology is everywhere, in our warehouses, hospitals, and supply chains. And yet, it remains poorly understood. Why is a tag red here, but not there? Why do performance levels drop for no apparent reason? To answer this question, we have the pleasure of welcoming Hadi Chehade, a doctor engineer in telecommunications and computer science. We often hear that RFID can read hundreds of tags instantly. So why do some tags sometimes read perfectly while others don't at all?
Great question. In reality, RFID performance depends on a set of physical parameters: the type of tag, its orientation, the material it is attached to, and the radio environment. In this episode, we'll look at 5 key factors, and more importantly, how to master them to make your installation foolproof.
Is it true that RFID doesn't need a line of sight?
Yes, that's true. Unlike barcodes, RFID doesn't need to be visible to be read. But be careful. When multiple tags are present at the same time, they all talk at once. This creates collision phenomena, and the reader has to handle them one by one. But with the right reader and anti-collision protocols, even hundreds of tags can be reliably read in a fraction of a second.
Why do some tags read better depending on their orientation?
It comes down to antenna polarization. Some tags have a linear antenna, others a circular one. If the field emitted by the reader isn't aligned with the tag, the signal doesn't come through well. Imagine the reader's antenna sends out waves like jump ropes vibrating in a single direction, linear. If the tag's antenna is aligned in the same direction, it captures all the energy. If it's perpendicular, you get radio silence. This is known as the cross-polarization effect. On the reader side, circularly polarized antennas are used. Instead of vibrating on a single plane, the wave rotates on itself. The result? No matter if your tag is tilted, lying flat, or upside down, it will always end up crossing the signal's path. On the tag side, this is where the manufacturer's expertise comes into play. Designing an omnidirectional tag, one that reads equally well horizontally and vertically, is a genuine technical challenge. Personally, I call this the art of RFID haute couture. The quality of a tag isn't judged solely by its raw reading range, but by its consistency. The best manufacturers design sophisticated antennas, often in a double dipole shape or with complex geometric designs, to minimize dead zones. A good tag is one that can maintain consistent performance at 360 degrees.
What if tags are stacked on top of each other? Does that cause problems?
Indeed, in RFID, there is not always strength in numbers. When 2 tags are too close together, stacked or overlapping, their antennas enter into electromagnetic coupling. In practice, they start talking to each other instead of responding to the reader. This phenomenon detunes the tag's resonant frequency. It's as if your radio slightly loses its tuning whenever a neighbor gets too close. The result? The signal gets smothered and reading range collapses. This is where trade secrets come into play. To counter this effect, engineers work on the very architecture of the antenna. Anti-coupling geometry. Some manufacturers design specific antenna loops, often figure-8 shaped or with compensation slots, that mutually cancel out the disruptive magnetic fields from neighboring tags. Adaptive impedance. High-end chips can adjust their own impedance to compensate for the detuning caused by nearby tags. Material selection, using substrates with specific dielectric constants, helps stabilize the electromagnetic field around the chip. My advice: not all manufacturers are equal. Don't choose a tag based solely on its open field datasheet. Always test it under real storage conditions, stacked in a box or on a pallet. That's where you'll see the difference between a component supplier and a true antenna expert.
Why doesn't an RFID tag always work on metal?
Metal reflects radio waves and disrupts the tag's resonance. A standard tag placed on a metal surface becomes virtually silent. On-metal tags, however, are designed with an insulating layer that corrects this problem. With the right tags, metal stops being an obstacle and can even become an asset, helping to propagate the signal even further.
Can the material surrounding a tag also affect the signal?
Absolutely. Some materials, such as water, absorb radio waves. But this phenomenon can also be turned to our advantage to detect a change, such as a liquid level. Here's a concrete example. I have here a water bottle fitted with a passive RFID tag. Currently, the tag is surrounded by air. The signal is stable and reading performance is optimal. Now imagine we fill the bottle. As soon as the water level reaches the height of the tag, the physical properties of the medium change. This is what is known as the sensing phenomenon. Water has a very different dielectric constant from air, which causes antenna detuning. This phenomenon now allows us to create liquid-level detection solutions with no physical contact whatsoever.
So if a tag isn't being read, does that mean it's faulty?
Not necessarily. It's often a matter of calibration between the tag, the reader, and the environment. This is precisely where UBI Solutions' expertise comes in. We tame these physical parameters to guarantee 100% reliability in the field. Choose the best supplier to support your project. Choose UBI Solutions.